Hello students, welcome to EPG Pathshala. I am Sumalay Roy from the Department of Physics and Astrophysics of University of Delhi. Today we are going to talk on module the Schrodinger equation in 3 dimensions under the paper Quantum Mechanics. So students, let us see what we are going to learn in this module. We'll learn the plane wave solution describing the motion of a free particle in 3 dimensions. We will know the orthonormality and closure relations of a free particle in 3 dimensions. We will study the behavior of a free particle confined by impenetrable walls of a 3-dimensional rectangular box. We will learn the degeneracy of energy levels of the particle in the case of 3-dimensional cubical box. We will study the eigenfunctions and eigenvalues of a particle in an anisotropic 3-dimensional harmonic oscillator. We will show the degeneracy of energy levels of the particle for isotropic 3-dimensional harmonic oscillator. Motion of a free particle in 3 dimensions. Extending the 1-dimensional non-relativistic motion of a particle in a time-independent potential Vx to 3 dimensions. Let us write the 3-dimensional equation in the form minus h bar square by 2m del square plus Vr psi r equals to E into psi r, where m is the mass of the particle moving in a 3-dimensional potential Br. To consider the motion of a free particle, we take V equals to 0. The Schrodinger equation 22.1 then becomes minus h bar square by 2m del square psi r equals to E psi r. This equation is separable in Cartesian coordinates and can be expressed in the form psi xyz is the product of 3 independent functions: x function of x, capital Y function of y, and capital Z function of z. By substituting this equation 22.2 and comparing both sides of equation 22.2 can be reduced to a set of 3 ordinary differential equations of the form minus h bar squared by 2m d2 capital X by dx square equal to Ex xx and minus h bar square by 2m d2y dy square equals to Ey yy and minus h bar square by 2m d2 capital Z dj square equals to EZZZ, with the condition E equals to Ex plus Ey plus Ez. We have already seen that acceptable solution of equation 22.4a exists for the value of Ex greater than equal to 0 and is given by capital X equal to a exponential I modulus of kx into x plus b exponential minus I modulus of kx into x, where a and b are arbitrary complex constants and modulus of kx equals to 2m ex by h bar square to the power 1 by 2. Plane wave states of the free particle. Proceeding in a similar way with equations 22.4b and 22.4c, we see that the 3-dimensional free particle solutions psi xyz equals to capital X x y as a function of y and capital Z z of the Schrodinger equation can be written as linear combinations of plane wave states. Psi r equals to c exponential I kxx plus kyy plus kzz, which is equals to c into exponential I k dot r, where the propagation or wave vector k has the Cartesian components kx, ky, kz, and c is the normalization constant. And from equation 22.5, we have E equals to Ex plus Ey plus Ez, which is equals to h bar square by 2m into kx square plus ky square plus kz square, which is equal to h bar square k vector square by 2m or p vector square by 2m, where p is the linear momentum. It is given by vector p equals to h bar into vector k. Plane wave states simultaneous eigenfunctions of energy and momentum. Wave state 22.7 is also momentum eigenfunction of the momentum operator p equals to minus I h bar del with the eigenvalue p equals to h bar k, where p and k are vectors corresponding to a definite linear momentum. The plane waves are thus simultaneous eigenfunctions of energy and linear momentum. More precisely, they are eigenfunctions of the Hamiltonian h equals to minus h bar square by 2m into del square, and of the three momentum operators px minus ih bar del x, py minus ih bar del y, and pz minus ih bar del z. Also note that the energy spectrum is continuous because every non-negative value of energy E is allowed. Moreover, each energy eigenvalue is infinitely degenerate, since the condition 22.8 only restricts the magnitude of the vector k so that there are infinitely many. Normalization of plane wave states. Possible orientations of this vector for a given value of E. The plane wave in 22.7 can be normalized by a simple extension of the procedure described earlier for the one-dimensional case. Thus, extending to the three-dimensional case, we have integration of psi k prime star into psi k r into dr, which is equal to delta k minus k prime, where the three-dimensional Dirac delta function delta k minus k prime is explicitly written as delta k minus k prime is equal to delta kx minus kx prime into delta ky minus ky prime into delta kz minus kz prime equals to 2 pi to the power minus 3 integration minus infinity to plus infinity exponential I kx minus k prime x into x dx into integration minus infinity to plus infinity exponential I ky minus ky prime into y dy into integration minus infinity to plus infinity exponential I kz minus kz prime into z total into dz, which is equal to 2 pi to the power minus 3 integration of exponential I k minus k prime dot r into dr. Assuming the arbitrary phase of the normalization constant c in 22.7 to be 0, we find that the plane wave states can be normalized as psi kr equals to 2 pi to the power minus 3 by 2 exponential I k dot r. We also note that the plane wave states 22.11 form a complete set so that any arbitrary state can be expressed as a superpositions of these functions, which in fact is the Fourier expansion discussed in the earlier module. The closure relation for the plane wave eigenfunctions is integration psi k star r prime psi k r dk equals to 2 pi to the power minus 3 integration over exponential I k dot r minus r prime dk, which is equal to delta k minus k prime. If we are to work with discrete eigenvalues, we restrict the domain of the plane waves 22.7 to an arbitrarily large but finite cubical box of volume LQ. At the walls of the box, they obey periodic boundary conditions. Plane wave states with discrete eigenvalues. A straightforward generalization of the one-dimensional treatment that imposes the condition that the three components of the wave vector satisfy the requirement kx equal to 2 pi by L into nx, ky 2 pi by L into ny, kz 2 pi by L into nz, where nx, ny, nz are positive or negative integers or 0. The energy E given by 22.8 can therefore take in this case only the discrete values. The momentum eigenfunction, which is 22.7, can now be normalized by requiring integration 0 to L dx into 0 to L dy to 0 to L dz multiplied by psi kr modulo square equals to 1. Thus, taking the arbitrary phase of the normalization constant to be 0, the constant c equal to L to the power minus 3 by 2, and the normalized plane waves are psi kr equals to L to the power 3 by 2 into exponential I k dot r. Particle confined in a three-dimensional box. These eigenfunctions form a complete set of orthonormal functions in terms of which any arbitrary functions can be expanded by a Fourier series within the Q. The three-dimensional box. As a second example, we turn over to consider a particle of mass m which is confined by impenetrable walls to move in a box of size L1, L2 and L3. The potential V inside the box is constant, which is taken to be 0, whereas at the wall it is infinite. This problem is considered to be a generalization of the one-dimensional square well discussed earlier. Boundary conditions on the walls of the box. The Schrodinger equation to be solved in the region inside the box is minus h bar square by 2m into del 2 del x square plus del 2 del y square plus del 2 del z square in the function x y z equal to e psi x y z. We must also impose the condition that the wave function psi x y z equals to 0 at each of the walls and beyond. Taking the origin to be one of the corner of the box and the wave function in the product form 22.3, we find that for 0 x within 0 and L1, the function capital Xx satisfies the equation minus h bar square by 2m d2x dx square equal to enx xx, and xx equal to 0 for x less than equal to 0 and for x greater than equal to L1. As in the case of one-dimensional case, the allowed values of E and x are given by E and x equal to h bar square by 2m pi square nx square by L1 square, where nx equal to 1, 2, 3. Energy spectrum of a particle inside box. Being the standing waves, x, capital X, the function of small x, is 2 by pi to the power half sine nx pi ln x. Proceeding in this way for the functions yy and zz, we obtain the normalized eigenfunctions of the three-dimensional case as standing waves psi n1, n2, n3 or nx, ny, nz equals to 8 by v to the power half sine nx pi by L1 into x sine ny pi by L2 into y sine nz pi by L3 into z, where v equals to L1 into L2 into L3 is the volume of the box and nx, ny and nz are positive integers. The allowed values of the energy E equals to Ex plus Ey plus Ez are E nx, ny, nz equals to h bar square pi square by 2m into nx square by L1 square plus ny square by L2 square plus nz square by L3 square. The energy spectrum, though discrete in nature, does not, however, exhibit regularities for general values of L1, L2 and L3. We find as the dimension of the box increases, the spacing of the energy level decreases, so that for macroscopic box spectrum is almost continuous. Energy levels in a cubical box. Considering the special case of a cubical box of side L, the normalized eigenfunctions are given by psi nx, ny, nz as a function of x, y, z equals to 8 by L cube to the power half sine nx pi by L into x, sine ny pi by L into y, and sine nz pi by L into z, where nx, ny, and nz equals to 1, 2, 3, etc. And the allowed energy levels are En equal to h bar square pi square by 2mL square into n square, where n square equals to nx square plus ny square plus nz square. The ground state is such that nx equal to ny equal to nz equal to 1, so that n square equal to 3 and the corresponding energy is E0 equal to 3 h bar square pi square by 2mL square. This level is non-degenerate. The next energy level has energy 2E0 corresponding to n square equal to c, which can be obtained in three different ways by choosing the set of quantum numbers to be 211 or 121 or 112. This level is therefore threefold degenerate. The next energy level can be obtained in a similar way. This is the energy levels, quantum numbers, and degeneracy. For different energy levels, there are, for energy E by E0, which is equal to 0, there is no energy level. For E by E0 equal to 1, there is only one energy level with quantum numbers 1, 1, 1, with a degeneracy 1. For E by E0 2, the quantum numbers nx, ny, nz are 2, 1, 1, 1, 2, 1, and 1, 1, 2, with a degeneracy 3. For E by E0 equal to 3, energy levels, degenerate energy levels are 2, 2, 1, 2, 1, 2, and 1, 2, 2. So the degeneracy is 3. Likewise for the higher energy levels. The three-dimensional harmonic oscillator. In the preceding slide, we have shown the first few energy levels of a particle confined in a cubical box. Shown are the quantum numbers nx, ny, nz. Of the corresponding eigenfunctions and the degeneracy of each energy level. The ground state energy is E0, 3 into h bar square pi square by 2mL square. The three-dimensional harmonic oscillator. Another example of a three-dimensional system for which we have Schrodinger equation separable in Cartesian coordinates is the motion of a particle of mass m for a three-dimensional harmonic oscillator potential Vr equals to half k1 into x square plus half k2 into y square plus half k3 into z square. By separation of variables, the separated equation in the form of one-dimensional linear harmonic oscillator can be written as minus h bar y square by 2m d2x dx square plus half k1 x square xx into ex x in x as a function of x, with a similar equation for y and z. Using the results of one-dimensional case, we get the energy spectrum to be discrete, the energy levels being given by E nx, ny, nz equals to nx plus half into h bar omega 1 plus ny plus half into h bar omega 2 plus nz plus half into h bar omega 3, where omega 1 equal to k1 by m into the power half, omega 2 is equal to k2 by m to the power half, and omega 3 is equal to k3 by m to the power half. And nx, ny, nz are positive integers or 0. The corresponding normalized eigenfunctions can also be easily obtained from the result earlier studied for one-dimensional linear harmonic oscillators. They are given by anisotropic harmonic oscillator. Psi nx, ny, nz as a function of x, y, z equals to capital Nx, capital Ny, capital Nz exponential minus half into alpha 1 square x square plus alpha 2 square y square plus alpha 3 square z square into h nx alpha 1x, h ny alpha 2y, and hNz alpha 3z, where hn psi is the harmonic polynomial and alpha 1 equals to k1 by h bar square to the power half and nx equals to square root of alpha 1 by square root of pi 2 to the power nx into nx factorial, with similar expressions for alpha 2, alpha 3 and nz. Note that for an anisotropic harmonic oscillator, where all the three force constants are different, the energy levels 22.30 are in general non-degenerate. However, in the case of an isotropic three-dimensional harmonic oscillator for which k1 equals to k2 equals to k3, which is equal to k, we have the potential given by Vr equals to half of k into x square plus y square plus z square, which is equal to half of k into r square. For this central potential, the energy levels of the three-dimensional isotropic harmonic oscillators are given by En equals to n plus 3 by 2 into h bar into omega, where omega is equal to k by m to the power 1 by 2, and the quantum number n is n equal to nx plus ny plus nz. Please note that here the number 3 by 2 comes because it is a three-dimensional harmonic oscillators. If you can remember the one-dimensional harmonic oscillators, there this number was replaced by 1 by 2. So for one-dimensional harmonic oscillator, the energy levels were given by En equals to n plus 1 by 2 into h bar into omega. But unlike to that, in three-dimensional harmonic oscillator, it is given by En equals to n plus 3 by 2 into h bar into omega. Now n here is an integer which can take the values 0, 1, 2, etc. till infinity. The eigenfunctions are given by 22.31, where alpha 1 equals to alpha 2 equals to alpha 3 equals to alpha equals to mk by h bar square to the power 1 by 4. The ground state has the energy, therefore E, which is designated at for n equals to 0, is 3 h bar omega by 2, which is not degenerate, while all other energy levels are degenerate. Please remember, in case of one-dimensional harmonic oscillator, this was E n equals to 0 equals to half of h bar omega, which we call a 0-point energy or ground state energy. Here, unlike to that, here it is a 3 h bar omega by 2 because here we are dealing with 3 dimension. We can see that the first excited state has the energy E n equals to 1 is 5 h bar omega by 2, and it is threefold degenerate, since it can be obtained in 3 different ways by taking the set of quantum numbers nx, ny, nz to be either 100 or 010 or 001. Here, what we have shown is the energy level diagram for three-dimensional harmonic oscillator, where the arrow shows along the y-axis shows the energy in the scale of h bar into omega. So the different horizontal lines explains the different energy levels. And we also noted the different quantum states, which is designated by nx, ny and nz on the middle, and the total number of states for each energy level gives you the degeneracy, which is tabulated in the extreme right hand side. So starting from 0, that means for the ground state energy, it is the nx, ny and nz all are 0. So there is the energy is 3 by 2. So the E by h bar omega is 3 by 2. That means here this is the ground state energy and there is no energy for E equals to 0. So the ground state energy is 3 by 2 h bar omega. And the quantum states for this is only nx equal to 0, ny equal to 0, and nz equal to 0. This is the one quantum state, so degeneracy is 1. Similarly, for the first excited state, for n equals to 1, it is E equals to 5 by 2 into h bar omega. So in the scale of h bar omega, it is 5 by 2. So this energy level, which corresponds to 5 by 2, can be obtained in 3 ways: 1, 0, 0, 0, 1, 0, and 0, 0, 1 for nx, ny, and nz. So there are 3 states which corresponds to the same energy 5 by 2 h bar omega. So the number of degeneracy here is 3. Similarly, for the second excited state, the energy is 7 by 2 h bar omega, or in the scale of h bar omega, it is 7 by 2 only. And the quantum numbers nx, ny, nz, the set of quantum numbers which gives this value of energy are 110, 101, 00011, 200, 020, and 002. That means there are 5 quantum states which gives the same energy 7 by 2 h bar omega. So the degeneracy is 5. Similarly, for the third excited state, is 9 by 2 h bar omega. And the quantum states, that means the possible values of nx, ny, and nz, which gives the same value of same energy level, same energy, is 111, 120, 102, 210, 201, 012, 021, 300, 030, 003. So the total set of numbers which defines the quantum states are 10. So this 10 quantum states gives the same energy 9 by 2 h bar omega. So total degeneracy is 10. Similarly for higher and higher energy levels. 3-dimensional isotropic harmonic oscillators. In figure 22.2 are shown the first few energy levels of the 3-dimensional harmonic oscillator along with their degeneracy. Note that the energy level En equals to n plus 3 by 2 into h bar omega. It is n plus 1 into n plus 2 by 2-fold degenerate, since this gives the number of ways by which n can take the different set of values from the sum of 3 non-negative integers nx, ny, and nz. The 3-dimensional isotropic harmonic oscillator serves another illustration of how the symmetry of the potential results in degeneracies. So student, let us see what we are going to learn in this module. We learn the plane wave solution describing the motion of a free particle in 3 dimensions. Note the orthonormality and closure relation of a free particle in 3 dimensions. Study the behavior of a particle confined by impenetrable walls of a 3-dimension regular box. Learn the degeneracy of energy levels of the particles in the case of 3-dimensional cubical box. Thank you.